to the Clean Water Lecture Series. My name is Rachel McKimmey, and I'm an AmeriCorps member serving with the Department of Environmental Conservation. This afternoon, we will hear from Joshua Faulkner, Research Assistant Professor with UVM Extension, who also coordinates the Farming and Climate Change Program in the UVM Extension Center for Sustainable Agriculture. In this virtual talk, Dr. Faulkner will discuss how climate change is impacting soil and water resources on farms and what management practices farms are implementing to mitigate the effects. Our next conversation will take place on Thursday, February 9th. Please join us then to hear an overview of Vermont's clean water progress from 2016 to 2022 from the Clean Water Initiative Program's 2022 Performance Report. Keep a lookout for more information on how to attend this event. You can sign up for our Clean Water newsletter to keep up to date on other events happening in the clean water world. A link will be posted in the chat. This lecture will feature a 20-minute presentation with question and answers at the end. You can ask questions by using the chat at any time during the presentation. We would like to respect everyone's time and end before 1 p.m. So we will be asking questions from the chat, and then if time allows, let people unmute and ask questions out loud. I ask that everyone please remain muted, and if you would like to verbally ask a question, you can use the raise hand function and we can call on you. At that time, you can unmute and speak. These three dots give you more options. So if you are joining from the application, you can turn on live captions. This lecture is being recorded and will be available on our YouTube channel after the event. And now I'll hand it over to Joshua. Please take it away.
Okay, thank you, Rachel. If you'll bear with me just a moment, I'll share my screen. I trust you can see that. If you can't, let me know. Great, let me minimize that. Okay, so good afternoon, everyone. Really good to be with you and talk about climate change, agriculture, and water quality in our state of Vermont. So just a little bit more of an introduction. So I am in a position, climate change and farming program coordinator, that was really formed after Tropical Storm Irene impacted Vermont years ago. And credit to UVM, I think, for developing this program, this position. I think we were the first land grant in the country to recognize the impact of climate change on agriculture and then act on that and actually devote resources to a position and a program. So it's been an exciting 10 years, and things are always evolving. But at the front of that has always been, trying to make farms more resilient and trying to limit water quality impacts on water quality impacts from those farms, and climate change certainly doesn't make that any easier. So I want to do just have limited time. Really looking forward to the conversation afterward. I'm going to try to keep this to about 20 minutes, my slides to about 20 minutes. But I want to talk about some of the key impacts of climate change on agriculture, then talk about some of the key strategies farms are using to adapt, and then also talk about some of our, maybe some of the more exciting research projects, applied research projects that we have that are focused in this space of climate change and water quality in agriculture. So, all right, let's jump right in. So just a quick review for some of you. I'm sure we know that in the Northeast it's getting wetter, and that sloping blue line across your screen is the Northeast as a whole. The increasing trend in average annual precipitation over the past 100 years or so. 100 years, an increase of about 4 inches. During those 100 years, not a big deal for farms, honestly. That's multiple generations on the farm, plenty of time to adapt, and farmers by nature are very resilient individuals. However, when you drill down into the climate district specific data in Vermont, you see a very different story, and that's what I'm showing with the text in your upper left-hand side of your screen, where when we look at the last 30 years, we see a very different story. We see increases of 5 inches in the southern portion of the state, 7 inches in the Champlain Valley, and 9 inches in the Northeast Kingdom. And so comparing that to 4 inches over a century, again, multiple generations, this is 30 years. This is potentially one generation on the farm. So certainly creates a challenge. That's almost a 25% increase in annual precipitation. This is having effects on farms. There's no question in terms of not only natural resources, which we're here today to talk about, but also in terms of production. And this is a pie chart taken from USDA Risk Management Agency data from 2001 to 2010, and showing really why Vermont crops fail, but these data are derived from where crop insurance payments are made. Excuse me. And as you can see, well over half of this pie is due to excess moisture. It seems to be the story in New England. When you move south out of New England or west out of New England, this pie starts to look very different. And honestly, drought is the slice of the pie that starts to dominate. But this excess moisture risk factor is definitely impacting us more than anything else here in New England. And then again, a little bit of review here. It's not just that we're getting wetter; it's that the trend, the patterns of precipitation are changing. And this is a figure taken from one of the most recent national climate assessments that shows that all around the country, really, we're seeing increases in very heavy precipitation events, but in no region is that increase to the degree that it is in the Northeast, where we're seeing this 74% increase in very heavy precipitation events, which are just point of reference is events over 1 inch in 24 hours. And I think what's interesting about this is that we work with a lot of farmers, and some may, there's various stances on climate change, and people are in different points in accepting the science, but no matter where they are, everyone agrees on this right here, that these we're getting more very heavy precipitation events than folks did when they were younger, perhaps growing up on that farm, or than their parents had when they were farming that land. So this is one place where we can all agree about, I think, changes in our climate. And these heavy precipitation events, of course, have impacts on the farm, and then those follow-on potential effects on natural resources. This is me standing in a cornfield, actually sweet cornfield, in 2015 after one single storm event kind of came through Chittenden County in the summertime, and I'm about 6'3", and so that gully I'm standing in is probably 2.5 to 3 feet deep, and I have a smile on my face because I'm a soil and water engineer by training, and I've really only seen gully erosion like this in graduate school studying events like the Dust Bowl. So this was kind of a little bit of a special moment to see this in person. Of course, tragic for the farm. These soils are the foundation of production, and they take years and years and years to rebuild this topsoil loss. And I have a modeling projection from a study done by some USDA scientists there at the top of the screen that I keep in mind, and it states that we'll see this disproportionate increase in erosion as we see annual rainfall increases. So if we think back to that first slide I showed, that was about a 40% increase in I'm sorry, about a 23% increase in annual rainfall in the kingdom. That would lead to then roughly about a 40% increase in erosion. So certainly something that we need to consider in this water quality work that we all do. And then it's not just losing soil from farms. It's literally for some farms, it's losing entire chunks of productive ground, um, portions of actual fields. And this is, in a state like Vermont, where we have the Champlain Valley, but then the remainder of Vermont is really very hilly, and composed of the farms that are there are a lot of hill farms, but then there's also these farms that are in the floodplain. These floodplain soils are, of course, very productive soils, very fertile, well-drained soils. I think crucial for local food systems in a state like Vermont, and given our topography. But these are also the soils that are in the crosshairs of climate change as we think about increased precipitation, increased frequency of extreme events, and the flooding that comes with those. This photo was taken by Vern Grubinger with UVM after Tropical Storm Irene in South Royalton. This is Hurricane Flats Farm. And then, of course, what kind of leading into what we want to talk a little bit more about today is that this soil that is lost from farms, of course, ends up somewhere, right? It ends up downstream, and this is a aerial image satellite image of the Connecticut River just after Tropical Storm Irene, and the Connecticut just belching out all this sediment, and of course the nutrients that go along with it into the Long Island Sound. Now, of course, all of that sediment and those nutrients are not from farm fields, but a fair amount are. And we see instances of this happening in the western half of the state as well, and in Lake Champlain. So this kind of frames the challenge for us. We know through some modeling work that the likelihood of increased total phosphorus transport to our water bodies is going to be increased with climate change, and certainly visual evidence like this and studies like this USGS study that I'm citing at the top support that modeling work. All right. So now I just want to change gears a little bit and talk about some of the key strategies that farms are using to address, that we're promoting and that farms are using to address these climate change challenges. And I think really at the core of that is really changing the way we manage our soils. We talk a lot about runoff and reducing runoff, and really when we think about soils, I think that's, we're kind of thinking about a little bit backwards. Really, we need to think about strategies that aren't reducing runoff, but strategies that are increasing infiltration, and that's kind of the way I like to think about this. And there are several, soil health is a pretty hot topic right now, and we could talk about that for quite some time, but I just want to kind of boil that down to three principles that I kind of keep in my head as I work with farmers and evaluate conservation practices that are being promoted. And one is constant soil cover. Preferably that cover would be living. It doesn't have to be just pure physical cover. Serves a lot of purposes. And so this is one of the kind of foundational principles behind a lot of our conservation practices, like some of the tillage practices that leave residue on the soil, cover crops, for example. There's several others as well. Another kind of foundational principle is really trying to build organic matter in soil. And organic matter is important because organic matter is really the food source for the soil organisms that build soil structure. And that soil structure is one of the things that is critical to increase the infiltration of water in that soil. So unless we have that organic matter, we're not going to be able to feed the biology that's going to build those healthy soils that are going to infiltrate water. Of course, building organic matter is, again, at the core of many of the conservation practices we promote, like cover cropping, root exudates, organic matter that gets incorporated into the soil profile, things like no-till that reduce loss of organic matter to the atmosphere. Others, and there's more than that. And then our third principle here is really reduce disturbance. So if we have a really well-structured soil, a healthy soil with lots of biological activity and organic matter, It's you know, they've kind of done their thing. They built a soil that can infiltrate water really well. Then soil disturbance is the last thing we want to do. And I know absolutely in some production systems disturbance is necessary, but we really try to minimize the amount of disturbance, because every time we disturb that soil, we disrupt those biological communities. We destroy some of those aggregates that are really key for soil structure, and then we have to build them back. So really, you know, this is again at the core of some of our practices, no-till primarily, and other conservation tillage approaches to just reducing disturbance of soils. And here's just one slide that I want to show that kind of brings a lot of these principles together. This is a rainfall simulator that I use, that I've used several years for my extension programming with farmers. And the idea, the principle behind this is taking slices from a farm and then raining on them. And there's a rainfall sprinkler just above the frame of this photo, where you kind of set these slices of soil on this table, rain on them, and then you capture the water that runs off in the buckets across the front, and you capture the water that infiltrates into those soils, and goes through those soils in the back, in the buckets in the back. And so those trays that those soils are sitting on are perforated. They have lots of little holes in them. And I just want to kind of walk us across this from left to right. So the soils, two soils on the left, are both from a conventionally tilled cornfield, and the only difference is the one on the right has some straw mulch on it. So this is really kind of hammering home that concept of keeping soils covered. This isn't a cover crop soil. This is just some residue, some straw mulch on that soil, and really prevented aggregate destruction, crusting from occurring, surface sealing from occurring. And then the proof is really in those buckets in the front, where on the left you see all that, lots more runoff from that soil, and then of course lots of sediment and potentially nutrients with that as well. And then the one on the right there, you see all of the water infiltrating through that soil into the bucket in the back. And then as we move from there further to the right, we have a poorly managed pasture, a well-managed pasture, and then a perennial hayfield. And you can kind of see that decreasing trend in runoff from those soils as well. Really all kind of a function of likely higher organic matter levels, and just less compaction as well as you move from that poorly managed pasture to that well-managed pasture. Okay, so that's kind of frames the rest of my slides here, which are about the research that we're doing now in Vermont, and I kind of want to set from watershed scale to field scale to plot scale, with one project in each of those buckets. And I'll start with watershed scale research. And so this is this project I'm going to talk about is called NRCS SEEP, which is NRCS is a program that's nationwide that evaluates conservation. SEEP stands for Conservation Effectiveness Assessment Program. And so we have one of these studies ongoing here in Addison County in Vermont. And the idea is to really evaluate the aggregate of lots of these conservation practices that build soil and reduce nutrient runoff at the watershed scale. So it's really exciting. This is a 10-year plus project that started in late 2019, early 2020. We are working with many state agencies on this, including DEC. USGS installed flow gauges for us in a few watersheds, 3 watersheds, and then we sample base flow and storm event samples from those at those stations. Just showing a photo of one of those stations there on the right side of your screen. We evaluate those for nutrients, and then perhaps as important, or maybe more important, is is that water quality data is critical, but it also is the documentation of what management practices are occurring within those watersheds, so that we can compare that management or potential change in management with the water quality signal. So that's a lot of groundwork there too that we're doing in those watersheds, documenting management practices. Here's our watersheds. I'm going to click through these pretty quick. Our treatment watershed is the Dead Creek, the West Branches and the East Branches in Addison and Bridport. And their control watershed is the Little Otter Creek in Moncton, Bristol, and New Haven. All right, and just one data slide from that study. We're in a calibration period right now. We're moving. We've just transitioned into our treatment period, but just wanted to show you 2 years worth of data, kind of the level of data that we're collecting, and we're just going to build on these data in the future. These are total phosphorus concentrations from those 3 watersheds, starting in March of 2020 all the way through October of this past October. That solid line, the light purple are base flow concentrations, and then the vertical bars are event concentrations. And so, kind of high level, you can take away a couple things from this. One is the general level of total phosphorus concentrations within these tributaries to Lake Champlain. And then 2, for me, which I think is especially important and related to climate change, is the clustering of events and higher event concentrations within our shoulder seasons, within the late fall and early spring. And so I think these are, good justification for these being really critical periods of landscape nutrient loss within these agricultural watersheds. And so more to come on this project as we move it forward over the next several years. And then the one factor that, before I jump into field scale studies, I just want to say, one of farmers' key adaptations to climate change is certainly, at least our row crop farmers, is subsurface drainage. And this is a very complicated practice. I don't think it's been painted as black and white. I don't think it is so black and white. I think it's very gray. I think that this practice is critical for production given climate change, but it also has the potential to reduce surface loss of soils as well, because we're creating more opportunity for infiltrating water within that profile as we drain water out of the bottom of that soil profile. But then there is certainly reason for concern, and it's days like this where we have a really severe summer thunderstorm, and I go to sample tile and I see this type of water exiting a tile outlet. And so there's lots of room for work on this to understand the true contribution of tile drainage to watershed P loading, and also how that affects the balance of P loading from a field, surface versus subsurface. So that's what's driving some of our work now. And we do a lot of field scale research on this. Just some images from the type of equipment that we use. We're digging manholes over top of tile lines there at the top left-hand portion of your screen. We're measuring surface runoff off the top of the field. Have lots of solar-powered monitoring infrastructure out there. I have I have 19 stations out in Vermont right now where we're doing a lot of this work, and it's extremely fun, but it's it's really challenging, especially given our climate in Vermont, where we have a lot of icing in the wintertime, and we know those are the critical periods for nutrient loss. So just one outcome from some of that field scale research, I just want to show this one. This is a study we did on a field in Addison County, and this is continuous monitoring of concentrations and development of mass loads from a tile outlet. This is from October of 2019 all the way through May into the summer of the following year, and then it really dried up. So we have pretty much an entire year's worth of data, a year's worth of loading data here. And what we found was that, and we've seen this in other studies as well, and when you sum this all up, we see about 1.4 pounds per acre per year. And this was a very typical management for a crop field on clay soils in Addison County. The interesting thing about this is that we really see about 96% of the total phosphorus load occurring during the vents. It's not that base flow, that slow drain of the root zone that's leading to any meaningful phosphorus loading. It's really the storm events because of those cracking clay soils. And then we're also doing some large plot scale work. This is Discovery Acres in St. Albans Bay. And this is a study where we're taking very large plots, and we have 4 of them. 2 of them have tile drainage, 2 of them do not. And we're monitoring surface flow and subsurface flow from all of these plots. Well, only subsurface flow from the plots that are drained. And so with this, we hope to answer questions about, again, what is that balance? What is the effect on balance of total phosphorus loss from a field when it's drained versus when it's undrained? And then also, what is the contribution of best management practices and different soil management practices on the loss of total phosphorus from a field? So this is a really exciting kind of outdoor laboratory where we're starting to be able to do some of those work and answer some of those questions. And then my last thing I want to talk about here are kind of, we have a lot of infield management practices that are we know are effective, but I certainly understand that there are probably going to be fields where those aren't going to cut it. Those are not going to reduce phosphorus to the levels that we want, phosphorus loss to the levels that we want. So we're also looking at edge of field filtration practices. This is just an image of one of those that would be installed on a tile drainage outlet, draining into a ditch, and in between that upper level of pipes and that lower level of pipes, we would install media with some sort of filter material in it that would bind soluble phosphorus to it. And we're built 4 of these this past summer, and we're evaluating those currently. Here's just an image of one on the left in a tile drainage at a tile drainage outlet in Addison County. And then one on the right, this is a ditch filter. So we know we have soluble phosphorus in surface flow as well. So is there an opportunity to filter that soluble phosphorus out of ditch flow as well? And so we'll be evaluating these 4 filters in the year to 2 years to come. So I know I went over a little bit. I apologize for that, but I'm going to go ahead and stop right there. That's all I have, and hopefully we have a little bit of time for questions.
We do have a couple questions in the chat. Somebody asked, in order to only lose productive ground once, what are your recommendations for the size/width of those healthy biologic covered buffer zones, which are adjacent to the water?
Let me open that up and make sure I understand what's being asked.
Sounds like they're asking about the size of buffer zones.
Size of buffer zones. Okay, like a riparian buffer zone. Great question. I don't know that I can answer that off the top of my head. What appropriate sizing would be. It would certainly depend on the size of the upslope field. Likely the typical concentration of phosphorus leaving that field, and the topography and flow regime, that passes through that buffer area. So NRCS and other agencies certainly have standard sizes in terms of what is are there dynamic guidance for sizing those buffers? There are some tools to do that, but unfortunately, I can't really answer that off the top of my head. I'm kind of on a field by field basis.
Another question that was asked is, can the end of pipe treatment systems handle high velocity flows during large rainfall events, or do they require more treatment time?
Great question. Yeah, so we do design those based on a hydraulic retention time. These are designed, the ones I showed you on my last slide were designed for a 10-minute retention time. We do have a bypass mechanism that if we have really high flows where we can't achieve that retention time, that those flows would bypass the filter and discharge directly. That is truly one of the challenges with these filter systems, are the high flows that we see in some of our tile systems. But we can capture, I would, off the top of my head, I would say that we can probably capture 75% of flows with that tile drainage filter system. And then those really high peak flows, we just have to let them go. We just don't don't have the ability to filter those, to hold them long enough to filter them.
Another question that was asked is the cost of trenching and tile installation seems like it would be enormous. Does your work include an analysis of return on investment?
There are very good tools for return on investment in tile drainage. Costs right now hovers around $1,200 to $1,300 an acre, and that often can be recouped by a farm in 5 years. So it's actually one of the things that pays back quicker than many other things in terms of production is tile drainage, and that's one of the reasons why so many farms are interested in tile, because it is so effective.
Another question is, can less phosphorus be used as fertilizer? Seems that would limit the phosphorus loss.
Yeah, good question. So most of the farms that I work with purchase no external phosphorus, no external inputs of phosphorus. That almost all of that phosphorus that they do use on their fields comes from manure that's produced on those fields, and they use it for the nitrogen value. And we do have they're also following nutrient management guidance and tools that limit the amount of manure that can be placed on those fields. Tools like the phosphorus index, for example, which we work quite a bit with here at UVM. So there's not a lot of phosphorus purchased to put on those fields. They're really using the manure that's on the farm. But then we also have tools that try to manage that phosphorus in the manure to limit the application in risky fields.
Do you know of research on different types of corn and forage that may be better for wetter conditions? Drying hay is a major challenge, as is getting corn germination with higher rainfall.
That's a really good question, and it's not something I can answer. I am admittedly not much of a plant person, so we do have agronomists within UVM that could help answer that, but I'm unfortunately not one of them.
Okay, here's one. Can you talk more about organic matter's effect on phosphorus runoff and how to build organic matter?
Yeah, so I'll start with building organic matter. So organic matter, so let's start with tillage. So tillage doesn't necessarily build organic matter. Tillage kind of stops the bleed of organic matter, stops the oxidation of organic matter from the soil. But tillage is very important for maintaining organic matter once you get it. In terms of building organic matter, that's primarily done through organic matter additions like compost and manure to the soil. And it's also done through use of cover crops, which exude carbon from their roots, and then those roots also remain in the soil, which adds organic matter to the soil, and also through um, increasing the amount of residue that's left on the field after harvest. So that plant matter, which we call residue after harvest, the more we can leave on that field, the more that will be incorporated into the soil, hopefully, and build organic matter in the soil. Those are some of the key ways we can build organic matter. In terms of impact on phosphorus losses, there's not a tremendous amount of work that is directly links organic matter increases to the degree of phosphorus loss. What we do have studies on are the practices that build organic matter and directly linking those practices to a reduction in phosphorus loss. And so that's some of the work that we're doing now at the field scale. That's exactly what we're doing. We're looking at how management practices are building soil health, but also at the same time, hopefully reducing phosphorus losses. So we have good data from other parts of the country, excuse me, and we're starting to build our knowledge here in Vermont on our clay soils as to sharpen our pencil as to the effect of those practices for phosphorus loss. We certainly expect it to be in the right direction, but we just don't know to what degree.
The broad implications of your research would seem to be that since wet weather is increasing, we need to sharply reduce tillage, preferably discontinue it altogether. But this is not what our farmers are doing. How does your research translate to policy?
Yeah, I would actually, I would push back on that a little bit. I would say even in my time in Vermont, 10 years, I used to drive through the lower Champlain Valley and see fall moldboard plowing happening on every single field that wasn't in hay that, as typical fall practice. Now you drive through there, I would say it's probably 25% or less of the fields that see that fall tillage. And a lot of farmers are moving toward maybe not necessarily no-till, which some farms are, but a lot of farms are definitely moving toward reduced tillage. It's a tricky situation to figure out for the farm because of, at least in the Champlain Valley, because of the clay soils we have. They're a really tough nut to crack. Um, and tillage, in some cases, farmers feel is absolutely necessary just to break that soil up because it can clot up so much and become so hard. But there are a number of many farms that are moving towards reduced tillage, if not towards no tillage. And I think it's just going to take time. It's not something farms can adopt overnight. Excuse me.
What can be done to reduce erosion in help fields? They have strips of bare ground between plastic strips.
Oh, great. So probably talking about vegetable systems here. Yeah, that's a really understudied area, plastic culture production and vegetable systems. You have this, this half of the field covered in plastic, which certainly produces runoff, and then the other half of the field is often bare. Really interesting work that I've seen in plastic culture systems is use of a living mulch. So planting a like a low growing clover in the alleys between the plastic rows. That will help, cover that soil, build organic, and do all those good things I just talked about on my soil health slide. That living mulch or potentially just a typical straw mulch as well. I've seen systems that have had success with both of those approaches.
It looks like I read that question wrong. They meant hemp.
Hemp. Oh, same answer. Yeah, for hemp. Yep.
Should we anticipate increasingly greater pollution of our waterways because of the cost effectiveness of the tile systems you mentioned?
Yeah, I mean that's a great question. I don't necessarily. I think the jury's still out. I think that's what places, studies like Discovery Acres, where we're looking at untiled versus tiled. Um, I, those studies are going to help us answer that. We hear from farmers a lot, and I've seen this myself, that when tile goes in, we see less evidence of surface erosion. And so surface erosion can be severe, formation of gullies and a lot of loss of sediment and sediment bound phosphorus. We don't know, there's no studies in the country that really try to answer that question. And we hope to be able to do that at Discovery Acres in St. Albans Bay. So stay tuned on that one.
One more question in the chat. Oops. Are you seeing impacts of winter rainfall events instead of snow on runoff data?
Yeah, we see both. Yeah. Um, our data, our data from the water at the watershed scale is doesn't we can't well, I won't say we can't. There's a master's student that's working on that very question right now. It is not immediately apparent that we see lots of increased phosphorus loading occurring during the dead of winter because of falling events. Now, there is some work at UVM that has shown that at the watershed scale. It's not, and again, I guess I'll say it's not immediately apparent from air data that that is what is happening in these watersheds. We will learn more about that as this master student finishes up his data analysis. And as we collect more data, this winter is an incredible winter for winter rain events so far. So we'll have some very interesting data at the end of this winter to add to those existing data.
In Franklin County, I've seen a considerable amount of fields that were plowed up after the late harvest this year. Can you discuss the implications this has on pea loss and organic matter destruction, especially considering our rain/melt events so far this winter?
Yeah, not probably not a great thing for pea loss. I understand why farmers do it, because the spring can be so difficult to work those soils given often wet conditions. But fall tillage is certainly not something that is going to be great for reducing pea loss. We see freeze thaw action, which breaks up aggregates, and we see exposed soils to winter rainfall events. Not a great thing.
The three principles that you introduced are an excellent basis to guide on-farm best management practices. How can farms respond in a year like 2022 when late wet fall weather caused delayed cover crop seeding and reduced effect?
Yeah, always the challenge. And not just Vermont, but a lot of the kind of upper Midwest and the Northeast is what's the fall hold for trying to get a cover crop established. This is not my area, but there's been work done on methods for trying to get that cover crop established earlier, interseeding strategies. It's a really tough nut to crack. I In a good year, cover crops can be very effective. In a bad year, they may have very little to no benefit, and that's unfortunately the way it goes. But I would say our agronomists at UVM are working on strategies to hopefully get that cover crop established regardless of fall conditions by getting it planted earlier, seeded earlier in the year.
It looks like there are no further questions in the chat at this moment, but if anybody has any questions they would like to ask verbally, you can raise your hand and we'll call on you. Emily says, as always, an excellent presentation. Thank you, Josh.
Thank you.
I second that. Thank you. All right. I don't see any further questions, so let's wrap it up. Thank you very much, everybody, for joining us.
Thanks for the opportunity.